This is a butane molecule. There are 4 carbon atoms present and 10 hydrogen atoms. So butane has a formula of C4H10. Now chemists generally do not like to draw these hydrogen atoms, so they use the bond line formula which looks like this, right? Now if you look closely, you can see that all these carbon atoms are sp3 hybridized. So this is a tetrahedral unit, this is another tetrahedral unit. So it's made up of 4 tetrahedral units, right? Now these tetrahedral units, they are connected by a single bond. They are connected by this single bond, and we can actually rotate these single bonds. So I can take this molecule and rotate the first carbon-carbon single bond, or the second one, or the last one. In fact, I can rotate all the single bonds present in this molecule. Let us now see what happens if I try to rotate the molecule about this single bond. So this is the single bond that connects the second carbon with the third carbon atom, right? So let me take my molecule once more and let me just rotate this bond. So now if I remove all these hydrogen atoms, a butane molecule can also be represented like this. Butane thus comes in different flavors. So a butane molecule can be represented like this, which is typically what you draw, the zigzag formula, but it can also be represented like this, right? Now these two molecules, they have the same molecular formula, but because they are different, so obviously they are isomers of each other. However, we have seen that if I simply take this molecule and rotate this about this carbon-carbon bond, I'll get my other molecule. If I simply take this bond and if I rotate it, I'll get this molecule, right? So such kind of isomers which can be converted into each other by simply rotating the molecule around the single bond are called conformers of each other. Conformers. Now in organic chemistry, whenever somebody asks you to draw butane, I'm pretty sure that you typically draw it like this rather than like this, right? So this video is all about trying to answer this particular question. Why do we prefer these zigzag lines to represent butane rather than representing it like this? The answer to our question lies in the energies of different conformers of butane. Now to study these energies, it kind of helps if we look at the butane molecule from the front rather than from the side. We can then draw the 2D projection of this particular molecule, and this is going to look something like this. This sphere represents this carbon atom out here, and to this carbon atom we have 2 hydrogen attached like this. So there are 2 hydrogen atoms attached out here, and on top we have this methyl group, right? So there is a methyl group on top. Now exactly behind this carbon atom there is another carbon atom, this one. So this is exactly behind, we cannot see it from the front. And to this carbon atom there is also these hydrogen atoms that are attached, so we draw them like this, and on top we again have a methyl group. So this is a 2D projection of this 3D molecule, and these kind of projections are called Newman projections. Now in this 3D molecule, the bond angle out here is your tetrahedral angle, so that is 109.5 degrees, right? However, when we draw the projection in 2D, this bond angle is actually 120 degrees. So do remember that even though in the projections the bond angles look 120 degrees, in reality all these carbon atoms are sp3 hybridized, so the bond angle is actually 109.5 degrees. We can now rotate the front carbon atom, and in this way we will get different conformers of butane. We will then draw the Newman projections and try and figure out how their energy varies. Let us start with this particular conformer, and let me also draw the Newman projection on the side. Now in this particular molecule, let us try and see the kind of repulsions that might be present to get an idea about the energies. Now if you look at this carbon hydrogen bond, there are 2 electrons out here, right? And similarly, even in this carbon hydrogen bond, there are also 2 electrons. So there can be some sort of repulsion between these two bonds, between the front carbon hydrogen bond and the back carbon hydrogen bond. This kind of repulsion, we call it the torsional strain. So we call it the torsional strain. Now such torsional strain is also present between these carbon hydrogen bonds, the one behind this carbon and this one. So there are some torsional strain out here also, and also between these bonds, these carbon carbon bonds. So do remember that the torsional strain is nothing but the repulsion between the electrons of the bonds at the front to the electrons of the bonds present at the back. Besides torsional strain, there is also another kind of repulsion present in this molecule. If you look at this group, it's a methyl group. So I have a methyl group on top on my right, and I have another methyl group on top on my left. Now these methyl groups, they are bulky, right? They are big and bulky. They are not simply hydrogen. And these bulky groups, as you can see, they are placed pretty close to each other. They are almost into each other's face. So there isn't sufficient space for both of them, so they kind of hinder each other. Such hindrance is called steric hindrance, and the repulsion arising out of such hindrance is called steric strain. Steric strain. And steric strain is sometimes also referred to as van der Waals repulsion or van der Waals strain. Do note that such kind of steric strain is not present between these hydrogen atoms because these hydrogen atoms are not sufficiently large enough to cause steric hindrance, and so there is no such steric strain. We are now ready to look at the energy profile of all the conformers of butane. So let us start with this particular conformer in which all the bonds are parallel to each other. Let us call this our conformer 1. Now if I take this front carbon atom and if I rotate it by some degrees, I am going to get a new conformer, right? I can rotate it by 1 degrees or maybe like 7.5 degrees, and in this way I can have infinite such conformers. Now to understand the energy of all these conformers, it's actually not necessary to draw all of them. We can draw a few of these and get the whole picture. Let us see. Let us take this front carbon atom and let us rotate it by say 60 degrees. So if my angle of rotation, which is called theta, is equal to 60 degrees, then this CH3 group is going to come out here, right? Because this whole angle is 120 degrees. So it's going to come exactly at the middle. So this is my second conformer. Now if I rotate the front carbon atom by another 60 degrees, so if I take this carbon atom and if I rotate it by 120 degrees, then this CH3 group is going to end up here and my conformer is going to look like this, right? So now if I keep rotating the front carbon atom at these intervals of 60, so if my total angle of rotation is 180 degrees, then my conformer is going to look like this. If the total angle of rotation is 240 degrees, then my conformer is going to look like this. If it's 300 degrees, it's going to look like this. And ultimately, if I take my front carbon atom and rotate it by 360 degrees, then I'm going to come back to my original conformer, right? So these are the 6 different conformers that I have drawn. But do remember, I can have infinite more conformers in between each of these intervals. Now if you look at this first conformer, then all these bonds, they are parallel to each other. So there is going to be a high degree of repulsion between the electrons in this front bond to the electrons present in the back bonds. And so we can say that this particular molecule is going to have a high torsional strain. Now as I keep rotating the front carbon atom, if I rotate it by even 1 degrees, then this front bond is not going to be parallel to the back bond anymore. And so the repulsion between these front bonds and the back bonds is going to decrease. In other words, the torsional strain is going to decrease, and it is going to keep on decreasing till I rotate the molecule by 60 degrees. After I've rotated the molecule by 60 degrees, the angle between these front bonds and the back bonds, these are also going to become 60 degrees. And now if I rotate the front carbon atom by even 1 more degree, then these bonds are going to get closer to each other again. And if my angle of rotation is 120 degrees, then they are going to ultimately become parallel to each other all over again, right? So if I look at these three conformers, the first conformer is going to have the maximum torsional strain. Let us say that the torsional strain out here is say 5 star, and this torsional strain is going to become a minimum out here. Let us say that the torsional strain is 1 star, and it will again keep on increasing and become 5 star out here, and decrease to 1 star again, and then again move to 5 star and 1 star and 5 star. Now these conformers, these ones 3 and 5, the front bonds are parallel to the back bonds, right? So we can say that these bonds eclipse each other. So this kind of conformers are called eclipsed. And these conformers, the conformer 2, 4 and 6, in these conformers the torsional strain is minimum, and this kind of conformers are called staggered. So 2, 4 and 6 are my staggered forms. All other conformer which is neither staggered nor eclipsed, and I can have infinite such conformers, right? All those conformers are called skew. Now if you look at the steric hindrance or the van der Waals repulsion, because these bulky groups are closest to each other out here, so this particular conformer is going to have a high steric strain. Let us say that the steric strain is 5 star, and as I keep rotating the molecule, this bulky methyl groups moves away from the other methyl group, so the steric strain is going to decrease. Let us say it decreases to 3 star out here, and as I keep rotating, the methyl groups moves even further away, so the steric strain is going to further decrease, and let us say it decreases to 2 star. And it is going to be a minimum when this methyl group is exactly opposite to the other methyl group, right? And let us say that the steric strain out here is 1 star. Now if I rotate the molecule some more, then in this particular conformer the methyl groups again start getting closer to each other. So the steric strain in conformer 5 is going to increase, and it's actually going to be exactly the same as in conformer 3, because in both these conformers the methyl groups are at 120 degrees. So the steric strain out here is also going to be 2 star. As I keep rotating the molecule, the steric strain is going to increase. The steric strain in 2 and 6 is exactly going to be the same, and it's going to be 3 star, and ultimately reach 5 star once I rotate front carbon atom by 360 degrees. Now if I look at our eclipsed conformers, let us start by looking at conformer 1 and conformer 3. Even though they are eclipsed, that is, they have the same torsional strain, but they have different steric strains, right? So their energy is going to be different, and this particular conformer in which the methyl groups eclipse each other, this is called the fully eclipsed conformer, while the conformer 3 in which the methyl groups do not eclipse each other is called a partial eclipsed. Conformer 3 and conformer 5 obviously are the same energy wise because they have the same torsional and steric strain. So conformer 5 is also a partial eclipsed. Similarly, if you look at our staggered conformers, conformer 2 and conformer 6 have the same torsional and steric strain, and they are termed as the staggered gauche, G-A-U-C-H-E, gauche, while conformer 6 has a lower steric strain compared to the other staggered forms because the methyl groups are anti to each other. So such a conformer is called staggered anti. Now if we look at all our conformers including the skew forms, then we can clearly see that this particular conformer, the staggered anti, this will have the lowest torsional strain as well as the lowest steric strain. So this is going to have the minimum repulsion, and so it is going to be the most stable amongst all the conformers of butane. So the most stable conformer of butane is not the fully eclipsed but the staggered anti, and this from the side gives us the zigzag structure which is generally used to represent butane.